Hey guys, welcome back. So now we're going to be talking about the mean value theorem. And the mean value theorem actually is really important in calculus, and it explains and proves a lot of things in math, but we're not going to get into its importance and all the boring proof behind it. We're just going to go ahead and see how exactly we can apply it. So let's go ahead and get started. So here we have that the mean value theorem is also referred to as blank, right? So we're going to give it a nickname, so I don't have to say mean value theorem 100 times. I am just going to say MVT. So that's going to be my nickname, MVT. All right. So the mean value theorem is actually a little picky. It has its conditions that it needs to be met, right? We call these the hypothesis also. And the MVT can be applied to every type of function, and it can be applied on every type of interval, right? They're going to give you an interval, and they're going to give you a function, and they're going to see if first is it worthy of using the MVT. So the first condition is that the function has to be continuous on the interval blank, right? So the function has to be continuous on a closed interval, which we're going to call from A to B, right? So it's going to be a closed interval from A to B. And by closed, I mean that I'm using brackets and I'm including the endpoints, right? So I'm including A and B in my interval. And we're going to say this is a closed interval. And we're going to refer this, we're going to apply this and show you what this means on my graph right here next to it. And it's going to be from 4 to 7, right? Which means I am talking about my function from this point right here, which is going to be, this is going to be my A, this is going to be my B, and then I look at how my function behaves from A to B. So I'm mainly focusing on how my function is all throughout here, right? So that's what I care about. And I'm going to be like, okay, is this function continuous? Sure, the function is continuous from A to B. It's nice and smooth, and there's no discontinuities. Quick reminder, our discontinuities are vertical asymptotes, jumps, or holes, right? And this function from A to B, we don't care about the rest of it, just from A to B has none of them. So we're good to go on the first checkpoint, and yes, our function is continuous that we have here, right? The next one is going to be, is your function differentiable on the interval, right? And the interval is going to be actually an open interval from A to B. It's going to be an open interval. And what exactly does it mean to be differentiable? This may be the first time that you hear this word, differentiable, but it's nothing new. Differentiable refers to that's derivative to differentiation, and this simply means, is my derivative continuous, right? So we're going to say that this right here is going to say is a derivative is f prime of x continuous. That's all I care about when I ask you if it's differentiable, right? And by the derivative mean continuous, you can look at it two different ways. One way you can be like, if I take my derivative, does it have any discontinuities, right? That is the most systematic way of doing it. You just take the derivative and then you see if it has any discontinuities. But what if you have a graph? What does it graphically mean to be differentiable, to not have a derivative, right? And we're actually going to refer to a differentiability as a smooth curve. A function that is differentiable is a smooth curve. So I'm going to go ahead and put that over here, smooth. So whenever I say that this function is nice and smooth, I mean that it's continuous and differentiable. It's going to be like my lingo that I'm going to use when referring to continuous and differentiable functions, right? And by being able to take a derivative just means that I can put a line tangent at every point from on my interval from A to B, right? So let's say I were just to try to put a line tangent here. Sure. I can take a derivative there. Sure. I can take a derivative there. Sure. Right? So those are times that I can take a line tangent. So, and if you guys can see, if I go around, you'll be able to do that just fine, right? And just to give you a quick examples of when it's not differentiable, right? There's mainly like 2 or 3 that you should always look out for, right? But I'm actually going to do some practice problems with things that are not differentiable. But just to give you a quick heads up on what they look like, right? I'm going to do them right here in green, right here on the side. So what I'm going to say is that you should look out for absolute values. Absolute values, for example, are not differentiable at 0. Because at 0, you cannot take the derivative from either side, right? At the bottom point, you just have like this weird derivative that you can't even take. So that's one. And then we're also going to have these type of functions, which they're common with like x to the second third, 2/3, x to the 2/3. That's another way of not being differentiable, because at 0 you can't take a derivative. It's kind of like, we call those sharp turns. We call the absolute values also sharp turns, or cusps, depending on how your professor wants to refer to them. And also when a function has a vertical tangent, right? And vertical tangent can also be referred to as a vertical asymptote. It's either or something like this, right? Like we just have like a function like this, and then we have another function like that, right? So at that point, whatever that is, whatever this point is right here, I cannot take a derivative because it's not continuous there. So those are the three types of common non-differentiable points. But we're going to do examples on those, so don't worry about that. I'm actually going to go erase that right now, because I actually have something else that I want to cover. And that's going to be how important it is to be differentiable, right? So being differentiable is actually really powerful, because there's a very good point that I want to make here, is that if your function is differentiable, right, it is automatically continuous. And let me show you what that means. Differentiable, which I'm going to say diff, automatically makes you can automatically assume that your function is continuous, right? So differentiable is very powerful. But continuous does not imply differentiable. So your function can actually be continuous, but it does not have to be differentiable. However, if your function is differentiable, it has to be continuous, right? So being differentiable is really powerful. So once we have proved that your function matches both being continuous and being differentiable, we're going to go ahead and talk about the whole conclusion of this theorem, right? So once we pass the first two hypotheses or conditions, we're going to talk about its conclusion of the theorem. And that means that there exists a point C where the slope of the tangent and the slope of the secant are different, equal, or reciprocal. And the whole point of this is to find a point C where the slope of the line tangent, which is going to be this right here, the slope of the line tangent is going to be this right here, slope of the line tangent, and the slope of the line secant, which is this right here, are equal at a point C, right? So equal. And let's go ahead and draw the slope of the line secant first from A to B. So it's going to be from here to here. That's some slope we don't know, some positive slope that we don't know. We're saying that there's a point C where my function where the slope of the line tangent is equal. Okay, but there's many slopes of line tangents, right? So I'm going to draw them all in red. So for example, what is the slope of the line tangent here? It's something, right? But it's clearly not the same as that slope in blue. So that would actually take forever to graphically see which type of slope would be the same. So what I'm going to do is I'm just going to draw, if you guys recall from algebra or pre-calc, when slopes are the same, that's another way of saying, right? When slopes are the same is another way of saying that lines are parallel, right? So you're wondering, why do I care about lines being parallel with the same slope? Look, we're going to use it right now. Because when the slope of that blue line, whatever it is, I'm going to look for parallel lines, right? So I have nothing below it. I only have my function above from it. So I'm going to go ahead and draw a bunch of parallel lines to my function. And I know I'm not going to be the best artist here, and my lines are not going to be the straightest, but you guys will get the idea. So let's go ahead and draw some lines that are parallel. Right? So I have one line there, one line there, one line there, one line there, right? So I just drew a bunch of lines. So if I number my lines 1, 2, 3, and 4, we can see that the point where the slope of the line tangent is going to be parallel to this one is going to be somewhere between line 3 and line 4, right? Which is somewhere like right here, somewhere in between. And that's actually going to be right up here. You guys see how the slopes are already looking parallel, but the point is actually going to be right there. And that is all we wanted to do. We wanted to find a point C where the slope of the line tangent at that point C, which is the meaning of this, is equal to the slope of the line tangent, right? And letter C, or our point C, is in between our interval from A to B. So you guys just see how A is here. Well, it's actually f of A, but this is just A and B, and then your C falls between it, right? So your C has to fall between your interval from A to B. And that's all we wanted to prove, right? That's all the mean value theorem tells you, that there's a point C where the slope of the line tangent, that blue thing on the top, is equal to the slope of the line secant, right? So that is the meaning and all, like the thinking behind the mean value theorem, the graphical representation. But now let's go ahead and do an example and how to actually do it, right? Before we just keep talking about what it actually is. So, and here in example 1, they're always going to start off with verify that the hypothesis of the mean value theorem is satisfied on the given interval, right? That is a common way of starting these problems. And what that simply means is that we just want to make sure that our two conditions are met. 1 has to be continuous on the closed interval. 2 has to be differentiable on our open interval, right? So let's go ahead and do that first before we even keep reading the rest of the problem. So we have our function here, which is f of x equal to x cubed plus 3x squared. Cool. Let's see if we meets the first condition, right? In which the function is continuous. Well, it's a polynomial, right? F of x is a polynomial, and a polynomial is always continuous. It's a polynomial, and polynomials are always continuous. So nothing to worry about. We didn't even need to look at our interval because a polynomial is continuous everywhere. So in this case, from -5 to 1, sure, our polynomials are continuous everywhere. So it is automatically continuous from -5 to 1. It's a polynomial. They're good functions, and you don't have to worry about the hypothesis too much. All right? So now we go to step 2, which is the derivative continuous, right? Which is the whole idea of being differentiable. Is a derivative continuous? Well, let's go ahead and take the derivative. 3x squared plus 6x. Cool. Well, that's another polynomial, right? And the domain of this polynomial is that this is continuous everywhere. So our derivative is also continuous everywhere. So when the derivative is continuous, we can say the function is differentiable, right? So differentiable. So you guys, we have now proved that the function is continuous and differentiable. And here's the good thing about this example. It applies to any polynomial function that you care about, right? All polynomials are going to be both continuous and differentiable, right? It gets a little more annoying when you see different types of functions, but for right now, we're good to go. So now that we have gone over hypothesis, right, which is our first condition and our second condition, then we can go ahead and apply the actual theorem. We can try to get our conclusion, which is find the values of C in the interval that satisfy the conclusion of the theorem, right? And what that means is I just want to find that point C where the slope of the line tangent is equal to the slope of the line secant, right? And remember that the C value that we get has to be in between -5 to 1. And here I put find all the values because it doesn't have to be only one value. It can be multiple values, right? Depending on your function. So let's go ahead and do this. So the first part that I'm going to do is, right, I'm going to do the left side, which means find f prime at C. Well, f prime at C is going to be a little simple for me to do because I already have f prime. So all I need to do is just put a C in there to find f prime of C, right? So I'm trying to get f prime of C is equal to f of B minus f of A over B minus A, which is right here, my whole theorem that I need to prove. So that's going to be 3c squared plus 6 times c, right? And I'm actually going to put those c's in red just to add a little emphasis that is exactly the whole point of this problem, to find what c is. So once I have found my f prime at c, I just put c into my derivative, which I already computed to check for differentiability. I'm going to go ahead and find f of b minus f of a over b minus a. So that's going to be finding f of 1 minus f of -5 over 1 minus 5. Cool. So first things first, I'm going to go ahead and compute f of 1 and compute f of -5, right? So computing f of 1, I'm going to do right here on the side, means I'm going to have 1 cubed plus 3x squared, right? And if you do that, you can do it on your calculator or in your head, that is going to give you 4. Now we're going to need to compute the other one, f of -5. Right? And if you do that, whether in your calculator or in your head, that's going to give you negative 50. Okay? So now let's go ahead and input that in here. So it's going to be 4 minus negative 50. Very important to make sure that we have the negative here and the negative here, and we don't mess up with that negative 50. That could just causes the whole problem, right? And then on the bottom, we're going to have a double negative. You see how we have 1 minus minus. So this minus and this minus are going to turn into a plus, and that's going to give us actually 6. Okay? And now the 4 minus minus is going to give us a total of 54, right? And then 54 over 6 is just 9, right? So here we have 3c squared plus 6c. But we're supposed to write all the way down, but we're going to be lazy and not. We're just going to like put a little arrow down, which means everything there is that. And now we have to solve for c, right? So we have 3c squared plus 6c equal to 9. Well, guess what? We have to factor here, right? So let's move over the 9 to the left and just factor. So I'm going to go ahead and do that just here under my hypothesis. So I'm going to have 3c squared. Let's get rid of the red. You guys get the point. We're looking for c. And before I even factor, I'm going to notice that all my functions, I'm going to notice that all my terms here have a 3. See here I have 3, 6, and 9. And I can take out a 3 from all of those. So I'm going to go ahead and do that while changing color. 3c squared plus 2c minus 3. Alright. So once I do that, I'm going to go ahead and just keep factoring. So I'm going to have c minus 3, c plus 1. The 3 is never going to equal 0. It's just a constant. Doesn't matter. This right here, when I set it equal to 0, when I have c minus 3 equal to 0, let's do it. Let's not be lazy. C minus 3 equal to 0. It gives me c equal to 3. And then when I have here c plus 1 equal to 0, it gives me c equal to negative 1. Negative 1. So you guys see that this problem kind of factored nicely, but all we really did was a bunch of algebra, and the only calculus that we did was setting the functions equal to each other. Alright? So our two values are 3 and negative 1. But the question is, which of these values are actually in our interval, right? Which values of c are actually in our interval? See, the first one, which is c equal to 3, is not in our interval because our interval stops at 1. So our only values of c that we care about is going to be just 1, right? So that could have been a really easy trick question that I could have put in there, because here I'm asking you for all the values of c in the interval, and I know the answer has 2 answers, but only one of them applies for the interval, right? So now let's go ahead and do another example that's a little different. And the main difference about this example right here is that I have changed my type of function, right? So polynomials are seen as the easy type of problems to do. Rational functions are always going to be a little more tricky, right? Because their domains are not all real. They're not always continuous. They just have their own problems to deal with, right? So we're going to start off this question the same way. Verify the hypothesis of the mean value theorem is satisfied. Cool. I don't know what that means. That just means do 1 and 2, which means am I continuous? Am I differentiable, right? So let's go with the first one, which says, is f of x continuous? Well, f of x is a rational. Okay, so whenever I have a rational, what do I care about? I care about setting the denominator equal to 0. Okay, so I set the denominator equal to 0, x squared equal to 0, or not equal to 0 for my domain. It's going to be x not equal to 0. It means that x is not continuous at 0, right? So we're computing the domain or its continuity, however you want to look at it. That means that I am not continuous at 0. Now, I am not automatically out of the game because I failed to prove that it's continuous everywhere, right? It can have its continuities. It can always be discontinuous. But the question is, does this discontinuity or this point of discontinuity affect my interval, right? The interval that I'm focusing on, is it affected by this discontinuity? Well, my discontinuity is at 0. I have a vertical asymptote at 0. Now, does that affect my interval? And yes, it does, because from -1 to 1, 0 is included, right? So quick little graph here, how this function looks like. If you guys don't recall, it is going to look something like this, right? So you guys can see that this function has a vertical asymptote, at 0. So it is not continuous from, let's say this is -1, and let's say this is 1. So from -1 to 1, it is not continuous. It is not, so I cannot use it, right? But let's say for some reason I would have gotten this wrong, and I would have been like, okay, cool. Let's say it was continuous, or I missed it, right? Is my function now differentiable at from -1 to 1? And the answer is no, because I cannot take a derivative at 0. I do not know what the derivative of my line tangent at 0 is. You guys see that? That is one of my 3, right? It was like sharp turns, cusp, or vertical tangents. This can be like the vertical tangent or the vertical asymptote. There's a vertical block in my derivative, which means that my derivative is also not continuous, therefore I cannot use it, right? So always look out for rationals in the denominator and see where it's continuous or not. But don't automatically say that because it's irrational you cannot use it, because you can use it if this continuity is not affecting your integral that you're looking at, right? So let's go ahead and do some practice problems on the mean value theorem. See you guys next time.